I'm trying to set up my presentation for this morning. If you bear with me, please. Here we are. Good morning, everyone. Thank you for the opportunity to do this keynote speech. The title of my keynote speech this morning is Transport of Nanofluids with Applications. I'm the Dean of Engineering. I'm Ali Chamkha. I'm the Dean of Engineering at Kuwait College of Science and Technology in Kuwait. The outline of the presentation this morning is we start with an introduction. Then we talk about various problems and nanofluid property models, applications, and representative forced, natural, and mixed convection problems. And then if time permits, we go over boundary layer flows and porous media using nanofluids. If we look about the sizes of particles, we have macro scale, micro scale, and nanoscale. If we're concentrating on nanoscale, for example, a DNA size is 2 nanometers. The buckyball is 1 nanometer. If we look at an apple, for example, at the macro scale, apple is 80 million nanometers. Diameter of a human hair is about 75,000 nanometers, etc. So in principle, the size guide, the water molecule is 1 nanometers. DNA is less than 3 nanometers. Proteins, 2 to 5 nanometers. AIDS virus, about 100 nanometers. The red blood cells, about 5,000 nanometers. The nanoparticles, in principle, we call them nanoparticles when they are in the range of 1 to 100 nanometers. Why nanotechnology is important? Nanoscale structures give rise to new properties and phenomena that are basic to macroscopic events. Nanotechnology can change the way almost everything is designed and made. The definition of nanofluids, why we call them nanofluids. Nanofluids are a new class of fluids that are engineered by suspending solid nanoparticles in traditional base liquids or heat transfer fluids that basically have low thermal conductivity fluids. Basic fluids, typical basic fluids are water, organic fluids, glycol, oil, ethylene, lubricants, biofluids, etc. Typical nanoparticles that are being used, metallic oxides like alumina, silica, copper oxide, etc. Staple metals like gold, copper, and silver. Nitrides could be aluminum nitride, silicon nitride, carbon nanotubes, diamond, etc. Nanoparticle size, as we said, between 1 and 100 nanometers. Why are nanofluids important? Throughout the lecture, you will see the importance of these, the effect of nanoparticles in fluids that are called nanofluids. Conventional heat transfer or base fluids have inherently poor heat transfer properties compared to most solids. Nanoparticles have unique properties that can be exploited to develop ultra-high thermal conductivity fluids. In principle, modern nanotechnology enabled the production of particles less than 50 nanometers nanoparticles. So in principle, we have a low thermal conductivity fluid. Then we have particles that have thermal conductivity in principle of that solid. We mix them together in a fully suspended particles that are fully suspended in the base fluid. And then once we have that, we will have the thermal conductivity of the so-called nanofluid will be much higher than the base fluid that's being used in industry. So therefore, here you will see thermal nanofluid heat transfer enhancement, thermal conductivity enhancement. The reports have shown breakthrough, substantial increase, 20 to 30% in thermal conductivity of a fluid, of a base fluid, by adding very small amounts, 3 to 4%, depending on the type of nanoparticles, of course, of suspended metallic or metallic oxide nanoparticles or nanotubes. Increased convection heat transfer characteristics for heat transfer fluids as coolants or heat flow. If we want to cool or heat, we can use nanofluids. If you take the simple pipe system like this, if we have nanoparticles and we have microparticles, in principle, nanoparticles remain suspended in the fluid, as you can see here in the picture, and therefore, while the particles settle and then tend not to be not to add to the thermal conductivity, and therefore do not enhance heat transfer, and they will cause lots of problems in terms of erosion and corrosion, erosion of the internal pipe material. In principle, you will have, for nanoparticles, you will have high, infinite, what do you call it, surface area, and much less for microparticles. If you look in terms of criteria, in terms of stability, microparticles settle in the flow when they are suspended in a fluid, while nanoparticles, the beauty about nanoparticles is that they are stable as long as they remain in suspension almost indefinitely in the fluid. Surface to volume ratio, it is 1 for microparticles. It's 1,000 times larger than that of microparticles for the nanoparticles condition. Thermal conductivity, it's low for microparticle, high for nanoparticles when used in fluids. The clogging of microchannel, as you could expect, microparticles do clog the channel, while nanoparticles, because they move along on the same streamlines of the fluid, they do not clog the microchannel. Erosion, because of their weight, mass, and bigger size, they will cause erosion. Microparticles do, and nanoparticles do not. In terms of pumping power, it is larger to pump microparticles than you would need for the nanoparticles. Okay, if you look at typical thermal conductivity for some fluids, engine oil, for example, is one. You can see it, and you cannot, for the scale shown, you cannot see it on this graph. Ethylene glycol, water, they have very low thermal conductivity. They are here. While alumina, you will have this. This is for alumina. Number 8, for example, for silver. Copper is heavily used in industry, and on the scale. Copper is number 7, which is here, much higher than water, of course. So this is why copper oxide is being used a lot. Now, for carbon, you see much, much higher thermal conductivity. These are types of nanoparticles that you can use in fluid. You enhance the thermal conductivity. If you look at this curve, thermal conductivity versus volume fraction, the amount of nanoparticles being added to the fluid, you can see this is for copper, for example. The solid, this one is old copper. This is the copper plus, this is fresh copper. And this is when you add little acid, you will see a tremendous increase in the thermal conductivity as you increase the volume fraction. And this is based on this 2-component mixture calculation of, this is the theoretical calculation, but in experimental calculations, you have slightly different. What affects the thermal conductivity of nanofluids? Thermal conductivity enhancement, or the things that add to the thermal conductivity factors are particle material, what is it made of, the particle size, big or small, shape, particle shape, I don't know if it's here, it's not there, but the shape is also important. Base fluid, where the nanoparticles are being suspended in, what fluid. The pH of pH also is important. Particle volume concentration, amount, temperature is important. Shape is another part, nanoparticle shape, whether spherical, cylindrical, or otherwise, is important as well. Potential benefits of nanofluids. Excuse me if I'm going very fast a little because of the number of slides that I have and the limited time that I have, so I'm going slightly fast. Energy efficiency, you will have improved heat transfer. That's the benefits of nanofluids. Improved heat transfer, reduced pumping power, lower operating cost, smaller, lighter systems like miniaturized heat exchangers, and cleaner environment because you reduce heat transfer fluid inventory. In terms of applications, the sky is the limit, but I will mention some here. Energy conversion and energy storage systems, electronics cooling technique, thermal management of fuel cells energy, nuclear reactors, combustion, superconducting magnets, biological systems, and biomedicine, and this heavily used on testing cases. Drug delivery in medical applications, heat exchanger systems. Now, if I look at an example, in a pressurized water reactor, nuclear power plant, the limiting process in the generation of steam is the critical heat flux between the fuel rods and the water. Using nanofluids instead of water, the fuel rods become coated with nanoparticles such as alumina or others, which increases the critical heat flux significantly. The use of nanofluids as a coolant as well in accidents, for example, in pressurized water reactor, could also be used in emergency cooling systems where they could cool down overheated surfaces more quickly, leading to an improved in power plant safety. Now, in automotive applications, engine oils, automatic transmission fluids, coolants, lubricants, and other synthetic high-temperature heat transfer fluids found in truck radiators, engines, and HVAC have inherently poor heat transfer properties. These could benefit from high thermal conductivity offered by nanofluids. Nanofluids as coolants allow for smaller size radiators and coolant pumps, and truck engines could be operated at high temperature, allowing for more horsepower. They also lead to the reduction of the frontal area of the radiator by up to 10%. This reduction in aerodynamic drag can lead to a fuel saving of up to 5% based on studies. If I go to electronic applications, cooling of microchips is a need for the computer business. A principal limitation for developing smaller microchips in computers is the rapid heat dissipation. However, nanofluids can be used for liquid cooling of computer processors due to their high thermal conductivity. In biomedical application, which is very important application, cancer treatment is very important. Iron-based nanofluids can be used in cancer imaging and drug delivery or radiation. Magnetic nanofluids can be used to guide the nanoparticles up the bloodstream to a tumor with magnets. It will allow doctors to deliver high local doses of drugs or radiation without damaging the nearby healthy tissue, which is a significant side effect of traditional cancer treatment methods. Now, unique properties of nanoparticles, as we said, size-dependent physical property, larger surface area, larger number density, and surface structure. Effect of nanoparticles is clustering, and the importance, as I said before, that the beauty about nanofluids is that the nanoparticles being suspended in the base fluid at all the time. This is when you get the most effect of nanoparticles. Lower enhancement of thermal conductivity for closely packed clusters. Agglomeration is a problem, and when they agglomerate together. High enhancement of thermal conductivity for clusters of particles separated by a liquid layer is better for that. If you look from this picture, look at the thermal conductivity versus volume fraction. If you have completely packed nanoparticles, they become bigger particles, and then you will see here there's no fluid between them. The thermal conductivity is low compared to more separated nanoparticles. This is, when you allow the fluid to go inside, like here, you will get more heat transfer effect. What problems nanofluids face? The rapid settling of these particles in fluid. If they settle and do not become suspended in fluid, this is a problem for the nanofluids. The small size of nanoparticles should improve the stability of the suspension. The agglomeration of nanoparticles is the biggest problem in cases that are being studied. Into larger particles that are found in liquids is a serious challenge. Agglomeration, nanoparticles being agglomerated with other particles, they become bigger particles and we cannot benefit from them. So sedimentation, settling, and agglomeration are the problems. What are the methods for dispersing particles? Coated with a surfactant, charged to repel each other in a liquid. Thus, if we use this, we alter the desired properties of nanofluids. We don't get the benefits we need. Mechanical dispersion method using high-speed disperser or an ultrasonic probe bath, it showed limited success. Methods for producing nanofluids, we have the two-step process. Nanoparticles are produced by inert gas condensation, then dispersed in a base fluid. This is used usually for excited nanoparticles. Unique one-step process, which is better. simultaneously makes them disperse nanoparticle directly into low vapor pressure fluid, and this is usually used for metallic nanofluids. Why nanofluids are investigated? Nanofluids have been investigated to identify the specific transport mechanism, to identify critical parameters, to characterize flow characteristics in macro, micro, and channels, to quantify heat transfer performance, to develop specific production management and safety issues, and measurement and simulation techniques, and others. In summary, for this part, compared to larger particles, nanoparticles have better suspension behavior, very large surface area and number density, and much lower kinetic energy due to the low mass they have. The measurement of thermal conductivity is substantially greater than theoretical prediction in reality. Now, what I wanted to do is I want to run through various types of problems that I have solved over the years using nanofluids, using different nanofluid models and different problems, and see the various things we found. Now, the first problem I talk about, run quickly about, mixed convection flow in a lead-driven inclined square enclosure with a nanofluid. Classical problem, a cavity with a lead-driven, this is the lead-driven heated surface, cold surface, etc., square cavity. The governing equations for those who work with nanofluids, they would know. This is the continuity equation, the momentum equation, and the energy equation in the streamlined vorticity format or formulation. These are the typical boundary condition for this problem. This is how we calculate the average Nusselt number, which are important. The important thing here is the property models that we use for the nanofluid. There are many models for the thermal conductivity. For example, if I go back here, you will see in the governing equations, you will see K and F. This is the thermal conductivity of the nanofluid. Kf, the thermal conductivity of the base fluid, etc. And the NF is for the fluid, nanofluid, and the others will be for the base fluid. So here you will see the thermal diffusivity definition and the density, the specific heat at constant pressure for the nanofluid, how we calculate it. Phi is being the volume fraction. We use, for example, for the dynamic viscosity of the nanofluid, we use the Brinkmann model, early stages, we use this. This is the viscosity of the fluid, base fluid, volume fraction. For the thermal conductivity model, we use the Maxwell-Garnett model. This is the model. And then we predicted these are some properties for the base fluid, being water here and alumina. You will see like the thermal conductivity 0.613 for the base fluid water, while it's 25 for the alumina. Mixing those together will give you a better performance in terms of heat transfer. These are typical streamlines and isotherms. For this is a mixed convection, so you will have a critical number which is called the Richardson number, which is I used here for small Richardson number for conduction cases, and then you'll have higher cases for Richardson number. This is for RI001, and I have other stuff. This conduction cases. You will see this is the inclination angle of the cavity. You will see that in principle, as you increase the volume fraction, you will have increase of Nusselt number. Now, this is the case of Ri=1 mixed convection cases. You will see as you increase, the Nusselt number increases as you increase the inclination angle from 0 to 90 degrees, as well as it increases as the volume fraction increases in this way, and they look linearly increased. Same thing for the case of convection, fully convection, and you will have the increased as the Nusselt number increases as the angle increases of the inclination angle and the volume fraction. Now, for another problem, we used, for example, for solar collector filled with a nanofluid. This is a schematic diagram of the solar collector. You will have the solar energy coming in from this way. This is the cover plate. This is the water alumina nanofluid. This is the wave-like absorber we were considering. And this is the cool surfaces. And this is insulation. And this is the hot surface coming from the radiation. Now, we calculated based on the basic principles of Navier-Stokes equations modified to use the nanofluid, as you can see here. And then these are the properties. Here we're using the same thing. This is the Brinkman and Maxwell-Garnett model, no changes here. But if we look at some of the results for different shapes, and you will see these are typical isotherms, and these are typical streamlines, and you will see the occurrence of multiple vortices in the system, which will affect the heat transfer. When they have the absorber have only one shape, no wave, you will see one streamline, one vortex enclosing the whole system. Same thing here, you will have different type of, now here we're varying the effect of lambda. And then if you look at the Nusselt number here, this is the nanofluid. You'll have enhanced heat transfer or energy collection using nanofluid. This is the radiation heat transfer. This is the base fluid heat transfer. This is the combined nanofluid stuff heat transfer. And this is the average temperature. It is enhanced using nanofluids. This is the average velocity. It's reduced as a result of nanofluids, and the same here. Now, if you go to another problem, which is the double lid cavity, similar calculations. The important here is use of different viscosity for nanofluid, different models. This is the original Brinkman model. This is the back and chew model that was used based on experimental data. This is still the Maxwell-Garnett model. So we used a different problem. We compared the Brinkman model and the back and chew model. And here we found interestingly different results. You will see in principle, the Brinkman model, you will have, as you increase the volume fraction of particles, nanoparticles, this is the Nusselt number, you will have enhancement in the heat transfer and the average Nusselt number. However, for the case here, you will see this case for RE equals 0.02 pack and show, you will see that as you increase the volume fraction, the Nusselt number decreases to a point before it starts increasing. And there's a critical condition. So it is not true, it's not a complete statement or correct statement to say that if you suspend nanoparticles in a fluid, you always enhance heat transfer. Sometimes you get the reverse effect. And this is an example. By using different model, we got a different result. And this is based, experimentally verified model. And we found for this case. So there are some conditions where the Nusselt number decreases as a result of adding nanoparticles. So the same here, you can see that it's not the same, whether you use the Brinkman or the back and chew. This is another trapezoidal model, nanofluids. And here, let me run quickly here, same types of models. And I want to show some things here. Okay, these we're using copper as the nanoparticles. I'm running quickly because I have other stuff to show. This is based on the aspect ratio of the trapezoid. You can see here the streamlines. And these are the isotherms. I want to go to the average Nusselt number. And again, you will see an enhancement in, you have reduction whether for the base fluid or for the nanofluid, as you increase the aspect ratio of the trapezoidal cavity, while you have enhancement in over the nano. If you use base fluid or nanofluid, you have enhancement for the Nusselt number. Here you have the Nusselt number again. With Prandtl number, you increase, it increases the Nusselt number as you increase the Prandtl number. And again, the nanofluid model has enhancement of heat transfer. Now, if I look at another more complex problem, now these are the area problems were slightly simple. Now here I have a complex problem where I have clear fluid, nanofluid being used here. Here I have a porous media, I have a cylinder that's rotating, permeable interface, and these are complex equations. And we have identified, we put epsilon and delta in this to have generalized model for whether, depending on the region, for different equations dominate a different region. So we put epsilon when it is 1, it is applies for the nanofluid layer. If it is epsilon, kept as epsilon, it's for the porous layer. Same thing for delta, 0 for nanofluid layer, and it's 1 for porous layer. And for the thermal diffusivity, it's alpha F for nanofluid, alpha FF for the porous layer. Of course, here you see the properties of nanofluid. And the most important here, we're using the thermal conductivity for the nanofluid, a totally different model that depends on the Boltzmann constant here and diameter of the solid DNP nanoparticle and diameter liquid molecule DF, and LF is the path, mean path for the fluid particle. This model is in the literature, we used it, and then we go to the result, calculate nano. These are the streamlines that you can see as this cylinder rotates. And here are the isotherms. I want to go to the Nusselt numbers. And here you see the Nusselt number because of the rotation. You will see that as you increase the rotational speed, 500, 2000, 6000, you increase the Nusselt number. And this is the radius for different radii. And this is the mean Nusselt number. You will see that as the radius of the cylinder increases, you will have increased Nusselt number. As you increase speed, you also increase in principle, increase the Nusselt number. Similar stuff. Now, if I want to go to another problem where we have a cavity with closed, you have a heated part, and everything here, this is cooled surface, and you're insulated, and you have the cylinder rotating inside, you have an opening. So we want to compare this system with opening and without opening. Similar type of equations. Here, the dynamic viscosity model we use is this. In the papers, you will find the reference for these models. And this is the thermal conductivity model we've used. This is the Brownian part, because here the thermal conductivity for the nanofluids is the static and the Brownian part, and these are added together. Again, the dynamic viscosity here is different. We have used a linearized thermal conductivity model like this that's based on the shape. So you will see the shapes that we considered were cylindrical particles, brick, and plate. I'll go to the directly to the results. These are this is the rotational speed, whether clockwise or counterclockwise, 0, no rotation, that's closed. This is partly open. These are typical streamlines and isotherms. Let's go here to the results of the Nusselt number. You will see here, in principle, you will see a reduction as you increase the speed. For these cases, you'll have a reduction of mean Nusselt number. However, if you look at the shapes of particles, whether sphere, the blue is the sphere, the red is the brick, and the cylindrical nanoparticles have the best effect, enhanced heat transfer over the other shapes. Same thing here. If you have the same thing here, you have the cylindrical is the highest mean, whether it's open, this is for partly open, and this is for closed. So similar effect, different values, of course. And here you will have the mean. If you have the volume fraction, you can see as you enhance the volume fraction of nanoparticles, you'll have enhanced heat transfer in terms of Nusselt number. Same thing whether it's closed or open. Now I go to an important problem, which is melting of nanoparticles, enhanced phase change materials in an enclosure, effect of hybrid nanoparticles. We use hybrid nanoparticles. This is a cavity that have phase change material, hybrid nanoparticle material, and you will have this is a heated surface and this is a cold surface, and you're doing this is with as the material, the mixture is here, melts, you will have liquid part here, you'll have a solid part that's not melted, and you'll have a melting front that's moving in this direction. And this is the diagram. This region where you have mixed solid and water. This is the mushy region. You have to model it differently. If you look at the model, this is the model, and you will have here, for example, everything. This is the viscosity of the hybrid nanofluid. This is the viscosity of the base fluid. What's different here is that S is the Kalman-Kosny model that expresses the effect of damping in the mushy region. In the Kalman-Kosny model, it is assumed that the region is a porous medium. The mushy region is called assumed as a porous medium, in which moving from liquid toward the solid part, the porosity and permeability of the medium gets lower, very low, and hence the velocity of the fluid tends to zero. And now phi of t here is the liquid volume fraction. These are the typical boundary conditions. Now here what we did, we had some data, experimental data, and we have linearized them to look like a linear curve like this in terms of a coefficient. We called it the viscosity coefficient, and in terms of volume fraction. And these are real data that we have modified. I will show you in a minute. We have also linearized the thermal conductivity data, and this is the thermal conductivity constant, etc. So these are the two models that are being used, and then the ratio of the thermal diffusivity for the hybrid nanoparticles, nanofluid. We have NC is the hybrid. NC comes as the the coefficient or parameter for enhancement of thermal conductivity. These are typical data. If you look at the results, I'll show a small video here. Here we have NC equals 0, MV equals 0. That is base fluid. We don't have any nanoparticles, 0 nanoparticles. So base fluid. Here we have volume fraction of nanoparticles 5%, and NC and MV coefficients of viscosity and thermal conductivity set to these values. You can see that when you have nanoparticles, you have faster melting. As you can see, the fronts moving in this direction. This is delayed for the base fluid. So you'll see enhancement in and this picture was the liquid volume fraction. As you can see, if you want to see it, we can see it one more time, as it is important. And you can see here the formation of the, now you're melting quicker than here. You have the recirculation zones, the mushy zone is here. Then you start movement, and then you can see this line. And then you finish it with only 5% of nanoparticles. Now here are some pictures for taken from the same color pictures for the base fluid without nanoparticles, and here with nanoparticles. And here you can see the melting interface that you saw as you are moving in the direction of melting. You will see these are the thing, and this is for different volume fractions, 0 volume fraction, and etc. Same thing here. Another problem we've solved is the using fluid structure interaction. And this is where we have a cavity and we have a moving oscillatory or oscillating fin. It's very important fluid structure problem. We can model it this way. You have hybrid nanofluid inside. This is the fin that is moving, oscillating. And then these are the main equations. These equations are for geometrically nonlinear elastodynamics. These are the this is the stress. Displacement, ds is the displacement. These equations for the solid fin and energy, while the arbitrary Lagrangian for 3, this is the of course continuity equation, etc. These are the arbitrary Eulerian formulation for the equations 3 to 6. We use the second Biola Kirchhoff's for the stress tensor, which is the stress here. And therefore, these are the governing equations, and these are typical boundary conditions. This is the interaction condition. And then this is the, not coming out, computational mesh. You can see how the mesh are changing as this fin oscillates. So you have different meshing. These are the experimental data that we found in for the thermal conductivity of hybrid nanofluid, and this is the viscosity, and that's what we modeled with a linear model. The results, you can see these are the results as the streamlines and isotherms during the oscillation. Again, these are when you change the elastic Young modulus of elasticity for the oscillator fin. Here you'll see how the Nusselt number as a function of time decreases. And here, before motion is set. Here, when you have motion, you'll have the oscillatory, the fin is being moving, and you will see this operation. This is the Nusselt number as a function of time for different times. Here you can see the colors, and you see the Nusselt number operation. Same thing here. Now, in principle, for this type of problem, as you enhance the volume fraction of nanoparticles, you have, in principle, reduction in the average Nusselt number due to the oscillation. Same thing here, you'll see for different Rayleigh numbers. As you increase, the Rayleigh number decreases except for high volume fraction. Then we solve some problems using conjugate heat transfer. You have, for example, this is a mixed problem, composite problems, where you have a clear nanofluids here, porous media here, and you have thick wall here, and that's conjugate problem. Similar treatment, except you'll have to take care of the conjugate part. Here we use different type of models for the nanofluids. This is the Yu and Choi model. This is the Korkine model, Brinkman model for the viscosity, and MG Maxwell Garnett model like here. And we try to see what type of results we get. And in principle, you see again the reduction of heat transfer or Nusselt number for this type of model, which is MG. And if you take the thermal conductivity model of Maxwell and Garnett, and you compare it with the Carnegie model for the viscosity, you'll see again the reduction that we saw in Pack and Chu model in the simple problem we showed. So again, I wanted to show here that it's not always when you increase the volume fraction of nanoparticles, you have enhancement of heat transfer. It depends on the model you're using. And here it raises a big problem, a big question. What type of model should we use? Which is more accurate? Which is the correct one? And that's something is left to be done in modeling, in finding models for nanoparticles, nanofluids. And these are the effect of a Darcy number. You will see here the Nusselt number increases as you increase the nanoparticles. The Darcy number. This and another problem is the semicircular cavity for a hybrid nanofluid. This is many people solve traditional problems like myself. We use cavities because easier to model. And now here we look at a circular cavity and with solid walls. So we have conjugate and we have hybrid nanofluids. Typical questions here. Now let me go directly to the results to save time. And the important, this is the model for the hybrid nanofluid. Now, if we look at the data, these are properties for copper, alumina, and water. Now here you see the results, and we go directly to the Nusselt number. And you'll see here that over time, the interface heat transfer decreases over time, while it increases as you enhance the Rayleigh number. Same thing here. This is the ratio, thermal conductivity ratio between the fluid and the solid, the thick wall. And then you see this effect here. Volume fraction. Here, as you enhance the volume fraction, you have enhancement of heat transfer. Similar stuff. Now I finished these type of problems. Now I have another interesting problems. I don't know if I still have time or not for the presentation, but I will run quickly for that, so I'll give you a flavor of that. Boundary layer flow and heat transfer of nanofluids over a flat plate. Typical problem. The objective, considered cases, the objective analysis of convective boundary layer heat transfer of nanofluids. Types of convection. We have forced convection on a horizontal plate, natural convection over vertical plate. the plate in clear fluid, whether embedded in porous media, whether we have nanofluids or not nanofluid. So various problems we considered, and we considered volume fraction, material of nanoparticles, size of nanoparticles, shape of nanoparticles, type of base fluid, working temperatures, many conditions. Now, these are the basic linear relations that I showed you in the melting problem, where we have linearized models for the thermal conductivity and the viscosity. And these are typical models that we use for this. And as you can see here, we use different type of nanoparticles, base fluid, kerosene or water, different sizes, different shapes. Now here they are all spheres. And these are real data, actual experimental data in the literature. And we model them to get the NC and V. I'll remind you with the parameters, NC and V for NC for the thermal conductivity and V for the viscosity. So we got the numbers we want, and then we plug them to find effects. So I'm not going to go through that for lack of time. These are the basic equations that we use for clear fluid, for nanofluid, and of course, this is for Darcy flow, and you see these, for nanofluid. Now here, the drift flux effects, you have diffusion phoresis, Magnus effect, shear-induced gravity effect, Brownian diffusion, which is very important, and thermophoresis. And for boundary layer fluid flow of nanofluid flow, these are the most important. They are found in the literature. And then these are the Brownian motion. These are the equations. I think I should not go through the whole thing because there are many. I just want to go for the sake of time because I know my time is up. Let me go directly. We did many cases. I'll go to the summary and then give you the summary from the results, the conclusion, if I can get to it. Porous media sizes. Okay. Conclusion. In conclusion, we found full similarity solutions were successfully achieved in all studied cases, considering the variable thermophysical properties, Brownian motion, and thermophoresis effects, and also correct boundary conditions for concentration equation. A new parameter, heat transfer ratio, we developed. Heat transfer coefficient of nanofluid over heat transfer coefficient of base fluid was introduced to show the enhancement of using nanoparticles in the base fluid. For clear fluid, we found smaller nanoparticles are better than larger nanoparticles for a clear fluid. Now, it differs for porous media. For rectangular nanoparticles are better than spherical nanoparticles. Again, for clear fluid, the higher working temperature, the lower the enhancement. If you increase the working temperature, you get lower enhancement. This is not good for nanofluids. Effect of type of nanoparticles is significant. In natural convection, deterioration of heat transfer can be seen. For clear fluids of forced convection, the drag ratio using nanoparticles, which we calculated, 5% volume fraction of alumina, 44 nanometers in kerosene shows 30% enhancement into convective heat transfer and 45% increase in the drag coefficient at the surface. 5% of volume fraction of alumina, 43 nanometers size nanoparticles in water shows 1% enhancement compared to 30. These sizes are very close to each other, but different. Kerosene or water, you have 1 here and 30% there. Enhancement in the convective heat transfer and 44% increase in the drag coefficient at the surface. Optimization, the optimum size of nanoparticles is between 5 to 7 nanometers for these studies that we did on boundary layer. In porous media, forced convection, in all studied cases, porous media, forced convection, nanofluid, the presence of nanoparticles increases the convective heat transfer. The smaller the nanoparticles, the higher the heat transfer. So better, lower nanoparticles are better in this case. Porous media, natural convection, that's forced horizontal plate. This is vertical plate, natural convection. In all studied cases, the presence of nanoparticles deteriorates the convective heat transfer. This is in total contrast with the forced convection here. The smaller the nanoparticles, the lower the heat transfer. This is in contrast with the forced convection as well. So whether you have forced or natural convection, you have different results for these cases. Future work, nanofluids development is still considered in research stage. Many factors need to be explored and optimized. Accurate nanofluids properties models based on experimental work are needed. Nanoparticles agglomeration, settling, erosion potential, etc. need to be addressed. Identification of heat transfer enhancement limits in different applications. Enhancement limits in different applications is desired. In exploiting the benefits of nanofluids, I can say in more applications, I can say that the sky is the limit. Thank you very much. This is my email in case you want to contact me. This is my website in case you want to see my work. Thank you very much for everything. And I thank you and thank the organizers for inviting me for this keynote speech. Thank you very much. Have a good day.